All right, so we have everyone here. I think we'll get started. Um, again, I just want to remind you guys that homework number 5 is due on Thursday, coming Thursday in 2 days. All right, so and then for number 6, due date tentatively now is March 4th. It might be changing depending on um, the progress we have in lecture. Okay, and then also for exam 2, that's the again it's the tentatively date for right now, might be changing. We'll see about that next week at some point. All right. So last time we talked about electric dipoles. So basically, if you have a system of two equal and opposite charge separated by a small distance L, then this system is called a dipole. Okay. So the dipole is equal to Q times L, the vector. So dipole is a vector, or sometimes called dipole moment. L is pointing from the negative Q to the positive Q. Many molecules, they are themselves are the dipoles. So for example, H2O, or if you have any like most of the asymmetric molecules like CO2, etc., or CO. For non-polarized, when you have let me go back just one slide here. So so for those molecules that have dipole moment, they are called polar molecules. Okay, otherwise they are called non-polar um, molecules. But in that case, if you have external field in present, then you can still make this non-polarized molecules being to become polarized molecules, okay, because of electrostatic interaction there. Under the influence of the electric field, a dipole can reorientate due to the electric force on the two charges. The torque it experience will be P, the dipole moment or dipole cross the electric field, okay? And then the energy change or the energy involved in this reorientation is P minus PE cosine theta, which is minus P dot product E, okay? For these two vectors dot product. And we also talk about if you have multiple point charges, then we learned this already, like for electric field at your point of interest, you sum over each electric field provided by each individual point charge, okay? And if you have charge distributions through a body, then you'll be doing integration, okay? You kind of divide the body into small slices. Each slice will give you a electric field at your point of interest P. So dE, derivative of E, is equal to K dQ, the charge of this small portion, divided by R squared times R vector, unit vector, to indicate the direction of the electric field, okay? So we can have different charge distribution. We might have line distribution. So if you have charge distributed through a line or a thin rod, then the charge density is called charge per unit length. So we use lambda for the symbol, all right? And then you can divide that line into small slices or small pieces. Then each small piece would have a charge of Q equals to lambda times dl. Okay, if you have a surface distribution of charge, then you can divide the surface into small pieces. Each small piece will carry the charge of sigma times dA. That's the dq. And then if you have volume distribution, then the charge per unit volume is represented by the symbol rho. Charge in that small piece of the volume is rho times dV in that case, okay? And then after you have done that for each scenario, you can do an integration through the line, through the surface, or through the body to get your overall electric field at the particular point P, okay? So depending on different scenarios, if you have point charges, then you summarize the electric field given by each charge, point charge. If you have a line, this charge distribution, you integrate through the line. If you have surface charge distribution, you integrate through the surface, okay? And then for volume distribution, you integrate through the whole volume of the body. All right. And we took a look on a couple of examples last time. So if you have a line distribution, if this line happens to be in the x direction, then the electric field will be in two directions, the x direction and then y directions. Okay, so this is a plane here. All right. So then x component is equal to either this expression or that expression. We derived this last time. Also for y component is either in this expression with cosine function or in this second expression here. Okay, given what's known, you can pick the expression that is most convenient to solve the problem. Okay. And we took a look on a second example when you have a line distribution. This time, the origin of the x is at the middle of this line here. So then the electric field over here, basically the equation you derive from the previous slide will be applied here. So this is the x direction, then this was the y direction in the previous case. But you can simply change the notation from y to z for this. Now, because of the symmetry in the x direction, the electric field will cancel out. So you only have electric field then in the z direction in this case, okay? And then we derive it to be in this expression over here, 1 over 4 pi epsilon times lambda times L divided by z square root of z squared plus L squared over 4. That's in the z direction. If you have L that is very long, compared to z, so then L can be approximate as infinity large, okay? So in that case, then the z square under the square root, if you add z square to L square over 4, okay, z compared to L is very small, then you can neglect the z square term over here. So then square root of in here becomes square root of L square over 4, which gives you L divided by 2. Okay, now you can see 2 will go above there, so it'll be 2 times lambda L divided by L. Okay, so L will cancel out, so then you'll have Z E electric field in the Z direction equals to 1 over 4 pi epsilon naught times 2 lambda over Z in the K direction. Okay, so in this case, K is perpendicular to X. Okay, if you are examining this situation in 3-dimensional, you can think about like X is in the direction of your thumb, then Z could be in this direction, right? Perpendicular to it, or it could be in some other direction. So then basically it says in the direction that is perpendicular to X, then this is your electric field, okay? If L is very large, if you have an infinity long wire here, then that's what you get, okay? So it's 1 over 4 pi epsilon 2 lambda over z. Z is the distance from your point of interest to the wire, okay? All right. So then in that case, we can extend the first example we checked last time into a 3-dimensional where z is aligned with the original x direction, r is the radial direction, okay? So radial direction, you can imagine this is in a full revolution. It could be, so it could be in this case, it could be in this case, and in this case, right? So it's the radial direction, any point that is away from this z direction, okay? So then E will be having a z component and then an r component, okay? So it will be any direction that is perpendicular to z. All right, so then you can have the two expressions again. All right, you just do the same here, k lambda over r, all right, instead of over y, and then sine of theta 2 minus sine theta 1. Okay, so in this case, it would be the same, k lambda 1 over r2 minus 1 over r1. Okay, and then in the radial direction, r direction, so it's minus k lambda over r. Okay, cosine theta 2 minus cosine theta 1 in that case. Okay. All right. Now, so we will take a look on one example here. So this one says if you have a charge Q that is uniformly distributed along the z axis from z equals to minus 1/2 L to positive L, 1/2 L. Okay, so basically this is your origin. This is minus 1/2 L on this end. This is positive 1/2 L. Okay, it's asking you to show that for larger values of Z, the expression for electric field of the line charge on Z axis approaches the expression for the electric field of a point charge Q at the origin. Okay. So that means, so this is Z, right? Point P to the origin is Z. So it's asking you to show if Z is very large. So that means Z is much larger than L, okay? So we can take a look on this one here. I think we can take a look on this one together. So basically you can apply the equation you get in the previous slide. So if you go back one slide there, you'll be looking at this equation, okay? So EZ, electric field in the Z direction is K lambda 1 over R2 minus 1 over R1. Okay, so then let's take a look. We can take the equation down. So E in the Z direction is K lambda 1 over R2 minus 1 over R1. So in this case, this expression would work better because we know R1 and R2. Okay, so let's take a look on the figure. So this is your Z equal to 0. This is the rod. I'm going to stop sharing my screen. We can take a look on the screen over here. Okay, so this is your point P, point of interest. This is Z. All right. So this is 1/2 L to here, and then 1/2 L to the other end. Okay. All right, so in the previous figure, this is so if this is your point of interest, this will be your R1. From here to your point of interest will be R1, okay? And then from here to here, this will be R2, okay? So then lambda will be equal to the overall Q divided by the total length, okay? So that's lambda, that's the line distribution of the charge. So then this will be equal to KQ over L times R2, 1 over R2. So 1 over R2 will be Z. R2 will be Z minus this guy, right? So Z minus 1/2 L. Okay. Z minus 1/2 L. Okay. Minus 1 over Z plus 1/2 L. Okay. So you'll have the Z plus this part. Okay. All right. There's some construction happening next door. All right. So then this is what you have, okay? So you're easy in this direction, okay? In the Z direction. So let's see, we can do this. So we can do KQ over L. On inside the parenthesis, we can do common denominators. Okay, we can do Z minus 1/2 L and then Z plus 1/2 L to be the common denominator. So then the first one will be Z plus L over 2, right? Minus the second one will be Z minus L over 2. Okay, so that's what you will get. All right. So then that becomes KQ over L. Here you have Z minus 1/2 L and Z plus 1/2 L. That will give you Z square minus L square over 2 square. Okay, that means 4. On the top here, you'll have Z minus Z, right? That cancels out, but 1/2 Z minus of minus 1/2 Z, that becomes 1/2 L minus 1/2 L, that becomes L, okay? So then in this case, you'll see that Z and L will cancel out, okay? So then your EZ, electric field in the Z direction, will just become KQ over Z square minus L square over 4, okay? Now, in the event that if Z is much larger than L, which is the assumption in this case over here, then you can approximate this as just KQ over Z square, okay? Which is your EZ, all right? That's the magnitude of your electric field if Z is much larger than L, okay? Or if Z is very large. So then this is becoming like similar to a point charge that is at the Q point charge Q over here, right? And then the electric field at this point would be just KQ over Z square, right? So which is that one, okay? So if your Z is much larger than L, then this approximate the electric field for the point charge at the origin, okay? Which is the what the problem is asking for you to show, okay? So we have just shown that, okay? Let me know if you have questions on this one before we move on.
Excuse me, Dr. Ho.
Yes.
How did so I understand lambda is the the linear
Right.
charge, but how did we solve for it in this particular situation? How did we get Q? Okay, so it's just I'm sorry, I just answered my own question. So it's the charge over the length of the rod, correct?
Right. Yes. You
Okay,
got
I'm
it.
sorry. Thank
That's
you.
fine. All right. All right. So we will take a look on a second problem here, example here. This one says, if you have a uniform line charge that has a linear charge density of lambda equals to 3.5 Newton of nanocoulombs over meter is on the z-axis between z equal to 0 and z equal to 5 meters. Okay, so this is what you have. I can sketch the problem for you here. I'm going to stop sharing in a few moments, but for right now, let me sketch the problem. So this is your z direction again. This where this is 0, okay, and then this is 5 meters. Now your line charge, your rod is sitting over here, that has a linear density of lambda equals to 3.5 nanocoulombs over meters. Okay, it says to find the electric field at z equal to 6. Okay, so here 6 z equals to or E equals to what's the electric field at this point? This is 6 point meters. And then at 9 point meters, what will be the EZ at that point? Okay. And then also at 250, so somewhere much further away, 250 meters EZ. Okay. So solve for those three. So this is A, this is basically B, this is basically C. Okay. You can again start with this guy here, E in the z direction is k lambda 1 over r2 minus 1 over r1. Okay, that's the equation you can use. So this is r2, and then this is r1. All right, from 0 to here, and then from here to there. Okay, so you guys can give it a try, and then we can take a look at the solution just in a few minutes here together. Okay. All right, I think let's take a look on this one together now. So for A, looking for the electric field there. So E in the Z component, all right, it's going to be K. K is the 8.99 times 10 to the 9th, okay? Newtons meter square over Coulomb square. Lambda, it tells you is 3.5 nano, so minus 9 coulombs over meters, okay? 1 over R2, in this case, R2 will be 6 minus 5, so it'll be 1 meters, okay? Minus R1 will be 6 meters, okay? That will give you just about 2.62 newtons over coulombs, okay, for the newtons over coulombs for the electric field. Okay, so that's part A. Part B, again, do the same easy, is equal to 8.99 times 10 to the 9th meter square over C square, the same lambda. All right, in this case, 1 over R2 now will be 9 minus 5 will give you 4. Okay, so 4 meters minus 1 over 9 minus 0 will be 9 meters. Okay, this will give you let me see. On my first one, this should be 26.2. Sorry about that. That's 26.2. Okay. On this one, this will be 4.37. Okay. All right. Similarly for C here, you can calculate easy equals to 8.99 times 10 to the 9th newtons times meters over coulombs square, 3.5 times 10 to the minus 9. Okay. Now 1 over, if you're at 250 meters, then your R2 will be 250 minus 4, which will be 246. Okay. Minus 1 over 250 meters. Or actually, this will be 255 because you are at 5 meters at one end. 250 minus 5. Also, yeah, that one is right. Okay. So then this will give you about 2.6 times 10 to the minus 3. Okay. All right. Also, it's asking you to compare this electric field to a point charge that is the same magnitude and sits at the middle of the rod. Okay, so at the middle of the rod, you are somewhere here. If you have a point charge Q here, okay, then what will be the electric field produced at 250? Okay, so that will be the R distance. R will be, so if this is at the center here, this will be 2.5, right? Where it's at 2.5. So then E at that point will be equal to KQ over R square, okay? So K will be 8.99 times 10 to the 9th. Okay. The Q will be lambda times L, okay? So 3.5 times 10 to the minus 9 times L will be the 5 meters, okay? Q will be lambda times L, the total charge. Divided by R square will be 250 minus 2.5, that will be the R, okay, squared, okay? Both are in meters down there. All right, so if you calculate that, this will be about, again, similar, like 2.6 times 10 to the minus 3, okay, newtons over coulombs, okay? So 2.57 to be exact, okay? In that case. times 10 to the minus 3. Okay, so you can see these two are equal to each other. Okay, so if you are very far away from your line distribution, then the line distribution of charge is approximately equal to a point charge that has the same total charge at that point. Okay, produced at that your point of interest. Okay. Any questions you guys might have on this one before we move on? You can just unmute yourself and then speak up. Okay. All right, so here is the conclusion that for large values of z, the expression for electric field of the line charge on the z-axis approaches the expression for the electric field of point charge that is at the center of the line. Okay. Next, we are going to take a look on if you have a ring, thin ring. So that's a line, but it's a circle in a circle, a line in a circle. Okay, so circular line. If you put that way. So then if the charge is uniformly distributed through the ring, what will be the electric field due to this charge at all points on the axis perpendicular to the plane through the center of the ring? So if the ring is sitting on the XY plane, then what's the electric field on the Z axis here where you are Z away from the center? Okay, so that's basically what the question is asking for. All right. Now this is a line distribution, charge distribution. Then again, we can divide the lines into very small pieces, many small pieces. So then for each of this small piece, the charge dq will be equal to lambda, all right, times the length of this will be the arc length of that. So times r times d theta. The theta will be in radians in this case. Okay, so r times d theta will be giving you this arc length, and then arc length times line density will give you the charge q. Okay, so you can see if you have a small piece over here, then the electric field it produced at this point p, okay, it's going to be pointing in that direction. All right. Now, again, due to symmetric, you can imagine that there's another small slices on this side over here, which will produce electric field in this direction. That is not exactly opposite, but in this guy goes in this direction, then this guy will go in that direction. If this is phi angle, this will be phi in the other way around. Okay, so then the electric field in the z component and then in the direction that is perpendicular to the z component would cancel out due to symmetric, right? So the resulting electric field should be just in the z direction. Okay, so in the x and y plane or in the xy plane, any directions, you will expect that there's cancellation or electric field for the other part from the ring, okay, opposite side of the ring that will cancel out, okay, due to the effect, due to symmetric. So total electric field on the z direction or at any point on the z axis will be just in the z direction, okay. So then we can just focus on the z component of the electric field. So let's take a look over here. Let me sketch the problem first. So there's a ring charge, all right? Not exactly, but x here, y here, z in this direction, all right? If you pick a small part of this ring over here, it will produce an electric field that is in that direction, E, all right? Now, let me move this over here. We'll just be focusing on the EZ here, okay? DE here, DEZ here, okay? This is DQ equals to lambda R d theta, okay? Where this is d theta, This is theta. Okay. Um, so then let's take a look on here. DE, we'll just focus on the magnitude. Okay, will be equal to K dq, right, over R square, right? So let me see other notations here. All right, so this is R here, and then this is Z here. So this guy, the R here, that should be equal to square root of Z square plus R square. Okay. And then if we call this as angle phi, that should be a fixed angle. Okay. So that's not a changing angle, but this is a changing angle. So this will be your variable here. So this equal to K dq is lambda R d theta. Okay. Over Z square plus R square, both Z and R are fixed. Okay. They are constant quantities, not variables. So then you can see this is the overall, this guy. Now for the Z component, right? So if this is angle phi, then we are doing cosine of phi. Okay, so then the electric field in the Z direction, that should be equal to dE cosine of this phi angle. Okay, so then dE in the Z direction should be K lambda R over square root of Z square plus R square, okay, times d theta times cosine of this phi angle. Okay, cosine of this angle will be equal to this divided by that, right? So you can rewrite that. So it's going to be equal to K lambda R over square root of Z square plus R square. Cosine phi is Z over square root of Z squared plus R squared times d theta. Okay. Now next for the electric field in the Z component, you'll be integrating of dEz, right? Now in this expression, you can see this K is constant, lambda is constant, R is constant, Z is constant. So the only variable will be d theta. Okay, so then you'll be just doing integration of, so put this, all these constant terms in front. So K lambda Z over Z square plus R square. Integration of d theta. Okay, so d theta goes from 0 degree to 2 pi. So from 0 to 2 pi. Okay. So then it becomes the electric field in the Z direction will be just becoming, so you are integrating d theta from 0 to 2 pi, that will give you 2 pi. Okay, so 2 pi from the integration there. So this will be 2 pi times K lambda R Z over Z square plus R square. Okay. And for this, you can see 2 pi times R, 2 pi times R will be the circumference, right, of this ring. And then if you do 2 pi times R times the line density, that will give you the Q, total charge Q. Total charge Q should be 2 pi R times the line density, right? So if you know Q, then you can replace that with just Q. So this becomes then KQ times Z over Z square plus R square, okay? That will be your electric field in the Z direction. Okay, and then that's also the overall or actually my bad. So here it's R square, so I've got to square here. Okay, so let's square here. So we should square this guy here. All right, square there. This guy remains over there. So then this square times this guy square root becomes 3 halves. Okay, z squared plus r to the 3/2 because this is z squared plus r squared to the 1/2. This is 1, so 3/2. So my mistake there. I apologize for that. But this will be 3/2, okay, at the bottom here. All right. And then the E field will be just in the Z direction. So then your E, if you want to include a direction, your E then is equal to KQ Z over Z squared plus R squared to the 3/2. That's in the Z direction, okay? Univector Z direction. All right. Let me know if you have a question about this one, okay?
Excuse me, Dr. Howe.
Yes.
On our final solution, it's KQ, is that a 2 or a Z? That's a Z,
Z,
right?
that's the Z.
Okay, that's what I
Yes.
thought. Just wanted to clarify. Thank you.
Yep, sure. All right. Now we can take a look if Z is very big. Okay, so if Z is large, then you can ignore this guy. All right. So if Z is, well, let me just stop sharing for right now. You can see it better here. So if Z is much bigger, say than R, okay, so that means Z is very large. So then E field then will be approximately equal to, in the bottom here, you'll just ignore the R because Z is much bigger. Okay, so then Z squared to the 3/2, that means Z to the 3rd. Okay, so this becomes Z to the 3rd at the bottom, and then KQZ times unit vector Z. In that case, this Z will bring this to the Q to 2. Okay, so it becomes Z to the square. Okay, so then Z will be from the point of interest to the center of this circle. Okay, if Z is really large, then it looks like this is KQ over R square. Okay, so that's the approximation you can take. If Z is very large, you can assume that all the charges at the center over here acts like a point charge. Okay, so that's basically what the note at the bottom of the slide says. Okay, so for large Z, the electric field is approximately the same expression as if there's an equivalent point charge sits at the center of the ring. Okay, so when Z is very big. All right. Now next we are going to expand what we just learned for a line ring, charge distribution in a ring to a disk. Okay, so basically now this time you are going to do just pick a small ring out of a disk, okay, which is r away from, or r prime away from the center over here. Okay, then for that ring we know already the expression for the electric field at that point. Okay, but this case that should be in the differentiation equation form. Okay, so I'm going to just show you guys here on this here. It's the based on what we just learned. All right, so I'm going to sketch it here for right now, and then I'm going to stop sharing so you can see a larger view on your end. So basically it says there's a ring or a disk, all right? And then you are again a Z away from the center of this disk. Now what you are going to do is divide the ring into the disk into small rings, okay, where this is say R prime away. circle like that. And then the thickness of the ring will be dr. Okay. So d of r, dr prime actually. So for that ring, the electric field at that point will be, you can say d EZ, right? Because we are taking a small part of the outer disk, okay? That would be equal to what we got earlier, which is this guy here. We can take that expression, so K, Q, Z. All right. Let me see. We should do DQ here because it's small q, okay? K DQZ over Z square plus, now in this case, your big capital R should be replaced by R prime. So R prime, okay? R prime square 3/2, okay? That will be your D E, okay? So then DQ, we can write DQ will be equal to, this is now line a ring with the thickness of that. So the area of this guy should be we call it dA. Okay, so it should be sigma times dA, where dA will be 2 pi r prime times the thickness of the ring. Okay, so it should be sigma times 2 pi r prime times d r prime. Okay, so you can replace dq with this expression over here. So that equals to kz over z square plus r prime square 3/2. Okay, dq will be sigma 2 pi r prime dr prime. Okay, this is your dez. Okay, let me stop sharing here so you can see a larger view on your end. Okay, so we are basically taking a ring of thickness of dr. Okay, and then this is circumference is r prime. So then the area of this small ring is 2 pi r prime dr prime. Okay, that gives you the charge on this small ring over there. Okay, that will give you the E electric field at that point. Okay, now for the overall electric field, it will be doing integration to both sides of the equation, kz over z square plus r prime square 3/2. Sigma will be the surface charge density 2 pi r prime dr prime. Okay, now for r prime, you'll integrate from r prime equal to 0 to the radius of this disk. Okay, so then will be from 0 to capital R there. Right, yes, it's capital R. Just making sure. Okay. So this is so you can put let's put the constant terms in front. Sigma times 2 pi and then kz. Okay, so we can do 2 pi sigma kz integration from 0 to r, and this is r prime of z square plus r prime square to the 3/2 dr prime. Okay, now over here you can see there's r prime here, there's dr prime, so we can do substitution, right? We can do let's do this. So if we do d r prime to the square, right? Then that will give you 2 r prime dr prime, right? So that means you can use this as your new variable, the r prime square. Okay, so then this is r prime there. Okay, so this becomes 2 pi sigma kz from 0 to r square of, this is 2 here, so you put the 1/2 over here, and then 2r prime dr prime, okay, which this is z square plus r prime square to the 3/2. Okay, we still have just that. Okay. All right. So this is on the top here. This is derivative of r prime. Okay, so then you can do substitution of if you say x equal to r prime square. Okay, so then this becomes dx. Okay, so then dx equals to 2r prime dr prime. Okay, so then this is dx. This is x. Right. All right. So then it becomes 2 pi sigma kz. If you replace that, this is 0 r square of 1/2 dx over z square plus x 3/2. Okay. So then it will become integration of this. This is 3/2 in the bottom. That means integration of, if you do integration, this is equal to 2 pi sigma kz. All right. And then 1/2, you can, let me see if you want to put 1/2 in front somewhere. So actually, integration of this guy will give you twice of, okay, 2 times. So it'd be 1/2 times 2 times a negative sign, okay, because this is, integration is inverse operation of derivative, right? So you can see what do you do for derivative of, so d over dx of 1 over z squared plus x to the half, okay? That will give you minus 1/2 times 1 over z squared plus x to the 3/2, okay? So basically then that will become, inverse of this will be giving you a minus of 2, and then minus, still minus of z squared plus x, okay? Now from z to the r square, okay? And then, okay, sorry about that. That should be 1/2 to the power at the bottom here. It's a little bit messy here. Let me use another piece of paper. So your EZ now should be becoming 2 pi sigma kz 1/2 times 2 minus of z squared plus x, okay, to the 1/2 power there from 0 to r square, okay. So then it becomes, so that cancels out, okay. So for r square, you put that r square over there, so it's minus 2 pi sigma kz minus 1 over z square plus r square to the 1/2 power in the bottom, minus, you put 0 in here, okay? So minus of a minus term, okay? Z square to the 1/2, okay? Then here you can distribute the z in, okay? So it becomes z here, that goes away, there's z there, okay? So 1/2 z squared to the 1/2 will be z, okay? So then minus minus becomes positive. So then this will be coming Oh, I shouldn't have a minus there. It's just from the above there. So 2 pi sigma k. All right. This guy minus or plus 1. So 1 minus this guy. 1 minus z over z squared plus r squared to the half power. Okay. This should be your final solution on this guy. All right. And then again, this is your e in the z direction. Okay. All right. Let me know if you have questions about this one. See if I can capture everything in one screen here. All right. I think we are going to just stop here for today. We just only have 1 minute left. Okay. So we can come back tomorrow for the just little bit remaining business over here. Okay. So let me know if you have any questions. Otherwise, I will see you guys tomorrow. Bye bye.